Hey guys, after talking about how to find the asymptote of rational functions, let's go ahead and jump into how to draft them. Hey guys and welcome back, Franck here, and if you like my video so far, go ahead and subscribe to my channel if you have not done so already. And today we are going to talk about how to draft rational functions. And so as you know from before, a rational function is a function that can be written as a division of polynomial. And so let me go straight into it and give you an example of it. So I'm going to have my first example here as f of x equals to 3x squared divided by x squared minus 4. And my goal here is to go ahead and draft this function. And so to draft a rational function, I usually go with 3 steps. I'm going to first find the x and y intercept. Then I'm going to find my asymptotes, all 3 of them, vertical, horizontal, and slanted. And finally, I'm going to get some extra points between my x-intercept and my vertical asymptote so I can know exactly where the draft is going. And so let's just go ahead and do that here. First thing first, this is a rational function, which means that we do not want the denominator to be equal to 0, which means x squared minus 4 should not be equal to 0, meaning x squared should not be equal to 4, meaning x should not be equal to plus or minus 2. All right, so what is my x-intercept here? My x-intercept is going to be the point where the graph meets with the y-axis. So I'm going to have y here equal to 0. And so with that, I'm going to set my entire function equal to 0. So you're going to have here 3x squared divided by x squared minus 4 equals to 0. And so if you multiply both sides by the denominator here, that's going to cancel. And what you're going to have is 3x squared equal to 0, which means that x equals to 0, with a multiplicity of 2 in this case because it's x squared, so 0 happens twice. And by the way, if you want to know more about multiplicity, I suggest that you check out my note 36, where I talk about how to draft polynomial function and talk about multiplicity in detail. And so next, I'm going to go ahead and find my y-intercept. That's going to be where the graph meets with the x-axis. So I'm going to set my x equal to 0 here. And so if I find my f of 0, that's going to be giving me 3 times 0 squared, that's 0, divided by 0 squared minus 4, that's negative 4, and that's equal to 0. After that's done, my second step is to find all the asymptotes. So in this case, since the function is already simplified, my vertical asymptote is simply going to be the places where the denominator is equal to 0, and that's going to be at x equals 2 and at x equals negative 2. And finally, to find my horizontal asymptote here, since the degree of the top and the bottom happens to be the same, you're going to get that your horizontal asymptote is going to be the division of the leading coefficient. In this case, it's going to be y equals to 3 divided by 1, which is equal to 3. And as far as the oblique asymptote goes, if you have a horizontal asymptote, you don't have an oblique one. You can only have one or the other, right? So in this case, you're done. And so if you want to know more about how to find asymptotes for rational functions, I suggest you check out my previous note, note 41, where I talk about that in greater detail. And the final note about asymptote is that you should know that the vertical asymptote is telling you about the behavior of the function wherever the function doesn't exist, so wherever the denominator is equal to 0, while the horizontal or oblique asymptotes are telling you the behavior of the function at infinity. So this is going to be the end behavior. And I'm going to show you how that works out when I go into drafting this particular function. And so my final thing that I need to do here, number 3, is going to be to find some particular points between the x-intercept and the vertical asymptotes. So I'm going to have to find here f of plus or minus 4. And so that's going to be 3, in parentheses, plus or minus 4 squared, divided by plus or minus 4 squared minus 4. And so that's going to be giving me 48 divided by 12. That's going to be 4. And also, f of plus or minus 1 is going to give me 3, in parentheses, plus or minus 1 squared, divided by plus or minus 1 squared minus 4, which should give me 3 divided by negative 3, which gives me negative 1. And so with all of this figured out, I'm going to go ahead and draw my plane right here really quickly. I'm going to have the xy plane here. And the next thing I need to do after I draw my plane is to go ahead and draft all the asymptotes. So I'm going to go ahead and draft them here. I'm going to have 2 vertical asymptotes, one at negative 2, and the other one at 2. And then I'm going to go ahead and draft my horizontal asymptote at y equals 3. Okay, so once you're done with that, you can go ahead and plug in all your points, the x-intercept, y-intercept, and your extra point, all of them. So I'm going to have my x-intercept here at 0, 0. And the y-intercept is the same thing, so it's still 0, 0. Then I'm going to put in my extra points. So I'm going to have the point of negative 4, 4. Then I'm going to have the point 4, 4. Then I'm going to have the point negative 1, negative 1. And the point 1, negative 1. All right, so those are all my points. And as you remember before, I told you about the asymptote being the guide for the function because it determines the end behavior of the function. So this is what I mean by that. This function has 2 vertical asymptotes, which means it's going to be drafted in 3 different portions because the vertical asymptote's job is to split the plane into portions where the pieces of the functions are going to go. So in this case, since you have 2 vertical asymptotes, you're going to have 3 different pieces for the function. All right, so on the far left here, the piece of the function that's going to be here is going to be right above the horizontal asymptote. The reason why I know that is because my extra point is right above the asymptote, and also there is no x-intercept in this particular portion. So if I were to draft the function below here, I would have no other choice but to cut the x-axis here, which is not good because we do not have more x-intercept right there. And so I have no other choice here even without the extra point, but to draw the function above the horizontal asymptote. So in this case, I'm just going to put an arrow right here to say that the graph is going to behave like this to go close to the asymptote. And I'm going to put another arrow right here to say the function is going to behave like that to go close to the asymptote. And so in the middle portion here, again, since I have 3 points below the horizontal asymptote, I know that my function has to be below the horizontal asymptote instead of above it. And so I'm going to go ahead and put arrows down here next to my asymptote to show how the function will behave as it gets closer to negative 2 and 2. Also, notice that my multiplicity for 0 here happens to be 2. So when I get to 0 here, I'm going to bounce like a parabola function because of the multiplicity. Finally, on the far right here, since my point is above the horizontal asymptote, and since I don't have any extra x-intercept, the graph has no choice but to be above the horizontal asymptote rather than below it. And so I'm going to have arrows here to show that the function will go up here forever, and I'm going to have arrow here to show that the function will behave like this. And so, as you can see here, the x-intercept and the extra points are like guides to tell you where the function is going to hit. But the asymptotes here are even more important because they tell you about the behavior of the function as you get to infinity or as you get to the points where the function do not exist. And so with all of that plugged in, I can just go ahead and connect all these pieces together and now I have my graph. And so for my first portion here, I'm going to follow the arrows here going to the point negative 4, 4. For my middle portion here, I'm going to go through the 3 points following the arrows on both sides so that I can get a parabola looking function. And on my last portion here again, I'm going to follow the arrows going to the point 4, 4. And with that, I will be done. Okay, and if you remember from my previous note, I told you that I was going to graph a function that has a hole in it. And so for this second example, let me go through that and show you how that will be done. I'm going to have here g of x equals to x plus 7 divided by x squared plus 4x minus 21. And so with that, you know already that the top is going to be x plus 7 and the bottom should be x plus 7 in parentheses and then x minus 3 in parentheses. With that, you can cancel out the x plus 7 and you're going to get 1 divided by x minus 3. So whenever you have a rational function and you are able to simplify it, you should do it because the graph of the original rational function is going to be the same as the graph of the simplified version of that rational function. The only caveat here is that the domain should come from the original function. So in this case, we're going to have the domain as x not equal to negative 7 and x not equal to 3. All right, let's move on. So we're going to have here, the first thing to do is to find the x and y intercept. So I'm going to have my x-intercept here, y equals to 0. And so if I set this function equal to 0, I'm going to have 1 divided by x minus 3 equals to 0, which multiplying both sides by the denominator is going to cancel it out and give me 1 equals to 0, which is impossible. So in this case, you do not have any x-intercept. Next, for the y-intercept, I'm going to have x equals 0, which means that g of 0 is going to be 1 divided by 0 minus 3, which is equal to 1 over negative 3. So you have a y-intercept in this case, right? And so notice that I'm doing everything on my simplified version, which is okay to do because they basically have the same graph except for those domain things. Number two, I'm going to go ahead and find my asymptotes. So for my vertical asymptote here, I'm going to have that x equals to 3 is where the function has a problem. And so that's going to be my vertical asymptote. And I'm going to not forget that I'm going to have a hole at negative 7 because that's not part of the domain. Next, my horizontal asymptote here is going to be y equals to 0 because the degree of the bottom is bigger than the degree of the top. And so since I have VA and HA, I do not have SA, the centered asymptote. And so I'm going to have to stop here for the asymptotes. Next, I'm going to go ahead and find some extra points. But to start with, let's go ahead and deal with the hole. So there's going to be a hole at negative 7. So g of negative 7 here, found from the simplified version of the function, is going to be 1 over negative 7 minus 3. That's going to be 1 over negative 10. That's good because that's going to show you exactly where the hole is supposed to be on the function. And so you have that. Then I'm going to go ahead and find g of 2 because that's between my intercept and my vertical asymptote. I'm going to have g of 2 equals to 1 divided by 2 minus 3, which is going to give me negative 1. And finally, I'm going to go ahead and find g of 4, which is going to be 1 divided by 4 minus 3, which is just 1. All right, so with that, I'm going to go ahead and draft all my asymptotes. I'm going to have x equals to 3 here. And then I'm going to have y equals 0 here. Since y equals 0 is the x-axis, I'm just going to put arrows here looking backwards to say that that's an asymptote. And then I'm going to go ahead and plug in my points. So I'm going to have the point negative 7 comma negative 1/10 right here. That's going to be a hole, so I'm not going to cover it all. And then I'm going to have my y-intercept at x equals 0 and y equals negative 1/3 right here. Then I'm going to have the point 2 comma negative 1, then the point 4 comma 1. And then as you know already, this graph is going to have two portions because there's one vertical asymptote. The first portion is going to be on the left of the vertical asymptote, and the next one is going to be on the right of the vertical asymptote. And so here, since all my points are below the horizontal asymptote, my graph is going to be here as well. And so I'm going to put arrows here and here to show how the graph would behave as I get close to the asymptote. And on the right here, I'm also going to put arrows here and here because I have a point above HA. All right, so now that I have all the markers down, I can just go ahead and connect all of these points and markers to draft my function. And so on the left side here, I want to connect all those points, keeping in mind that I should not go to the point negative 7 comma negative 1/10 because that's a hole, and following all the arrows. Then I'm going to connect all the points and arrows here on the right as well, and I would be done. All right, so let me give you one last example that has a centered asymptote inside so you can see how that works out as well. And so my last example here is going to be the function h of x equals to x cubed plus 1 divided by x squared plus 2x. And so with that, I can go ahead and simplify this function because the bottom has common factor. So I'm going to have x cubed plus 1 on top divided by x on the bottom in parentheses, x plus 2. And so the first thing I should do here is find my intercepts. So for my x-intercept here, y should be equal to 0. And so if you set the function h of x equals to 0, multiplying both sides by the denominator would cancel it out. And so you're going to have x cubed plus 1 equals to 0, which means x cubed equal to negative 1, which means x should be equal to negative 1. So your x-intercept here is going to be y equals 0 and x equals negative 1. Then for the y-intercept, you should know that x should be equal to 0. And since 0 is not part of the domain, you're going to have that there's no y-intercept. Next, we're going to be looking at the asymptotes. And so in this case, your BA, vertical asymptotes, are going to be x equals to 0 and x equals to negative 2. Also, HA, your horizontal asymptote, since the denominator has a degree of 2, and the numerator has a degree of 3, which is bigger, we will not have any HA. And so therefore, we might have an oblique or centered asymptote. And so I'm going to go ahead and do a long division on this particular rational so I can see its alternate form. And so if I go ahead and do that, I'm going to have x squared plus 2x right here. And then under the division sign, I'm going to have x cubed plus 1. So our leading terms here is going to be x squared and x cubed. Dividing those two together will give you x. So you're going to have x here. Then multiplying that by the divisor is going to give you x cubed plus 2x squared. Subtracting these two expressions would cancel out the leading terms. And all you're going to have is minus 2x squared plus 1. And so again, the leading term here is going to be negative 2x squared, which you can divide by the leading term of the divisor, x squared. That should give you negative 2. Then negative 2 multiplied by the divisor is going to give us negative 2x squared minus 4x. And subtracting these two again is going to cancel out the leading terms. And what you're going to have at the end is negative 4x, which is going to be 4x, and then plus 1. And so with that, you should know that your function h of x can be rewritten as x minus 2 plus 4x plus 1 divided by x squared plus 2x. And so since this rational portion of our function is going to go to 0 because the bottom's degree is bigger than the top's degree, we're going to have that y equals to x minus 2 is going to be our oblique asymptote or slanted asymptote. All right, so with that, there's one thing that I haven't mentioned yet is the fact that a draft is never allowed to cross a vertical asymptote, but in some cases, it could happen that the draft crosses a horizontal asymptote or slanted asymptote, which is going to happen in this particular function. So I'm going to show you how to find the location where your draft crosses your asymptote in this case. You're going to have to set the function and the asymptotes equal to each other. So I'm going to have here x minus 2 plus 4x plus 1 divided by x squared plus 2x, that's the function, equals to x minus 2. That's the slanted asymptote. And so I'm going to go ahead and solve for x here. The x minus 2 are going to cancel. Then you're going to get just the fractional part, 4x plus 1 divided by x squared plus 2x equals to 0. Then multiplying both sides by x squared plus 2x would cancel out the denominator. And so what you're going to have is 4x plus 1 equals to 0, which should give you x equals to negative 1/4. So in this particular case, you should know that the draft is going to intercept the oblique asymptote at x equals negative 1/4. All right, so for my extra points here, I'm going to have h of negative 3, which is going to be negative 27 plus 1 divided by 9 minus 6. That's going to give me 26 over 3 negative, which should give me 8.66666 forever negative. And h of 1 would give me 1 plus 1 divided by 1 plus 2, which should be equal to 2/3. And so with all of those asymptotes and points, I can go ahead and draw my plane right here really quickly, and I can go ahead and draft all of my asymptotes. So I'm going to go ahead and draft the vertical asymptotes first. At x equals to 0 here, that's going to be my y-axis, so I'm going to go ahead and put backwards arrow here to show you that that's my asymptote. Then at x equals negative 2, I'm going to go ahead and draft an asymptote there as well. Then finally, I'm going to go ahead and draft the y equals x minus 2 asymptote. That's going to be just the first diagonal shifted down by 2. So I'm going to have a point here at 0, negative 2. Then another one here at 2, 0. Another one at negative 2, negative 4. And I'm going to connect those out to get a line that is oblique or slanted. And so that's going to be my asymptote. So with these three asymptotes, I can go ahead and plug all my points. So the first one I'm going to go ahead and plug here is going to be my x-intercept. That's going to be the point of coordinate negative 1, 0. Then I'm going to have the point of coordinate 1, 2/3 right here. And finally, I'm going to have the point of coordinate negative 3, negative 8.66 all the way down here. And of course, I'm going to drop down vertically from negative 1/4 here to show you that my draft is going to cut the oblique asymptote right here. Okay, so with this, since you have two vertical asymptotes, you should know that your draft should have 3 different pieces. On the far left here, since my point is under the oblique asymptote, I'm going to know that my draft is going to be trapped here. So I'm going to put arrows here and here to show you the behavior of the draft. Then in the middle portion here, I know that my graph should go from left to right while going down. And so my arrows are going to be up here and down here. And finally, on the far right, since my point is above the oblique asymptote, I know that my graph should be stuck above the oblique asymptote instead of below it. And so I'm going to have arrows right here and here to show the behavior of the function. Finally, with everything marked down, I can go ahead and connect all these things to have my graph. And so for the first portion here, I'm going to connect these two arrows with the point -3, -8, 66. And then in the middle portion here, I'm going to go from the top arrow here, meeting the point -1, 0, then cutting the oblique asymptote here to reach my second arrow on the bottom here. And then for the right portion of my graph, I'm going to go ahead and connect these two arrows again while reaching for the point of coordinate 1, 2/3. And with that, we are done. All right. And so for my next two videos, I'm going to be talking about how to solve polynomial inequalities and rational inequalities. And as usual, if you like a PDF copy of this note, check out the description below. And if you like the way I break down the material, give me a thumbs up, and I will see you next time. Bye-bye.